Hello, everybody. So I don't need to introduce myself. Everything was said. So now we are going to talk a little bit about post-quantum cryptography, and we are making some researches. Most of them are in post-quantum cryptography field. And here I want to present the results of one of our researches. And it's a theoretical one, and also we have a practical implementation. It is, of course, a little bit complicated for some of you, and I will give you the necessary background. I will make the introduction, and afterwards, let's begin. So maybe for some of you it will be very boring, but let's quickly cover to understand everything what I'm talking about. So we have here, as always, our two heroes, Alice and Bob. 1 minute, sorry. Here it is. And okay, so first of all, they have to generate the key, and they share this key. Afterwards, Alice has her message, and she wants to encrypt it. So she needs encryption algorithm for it. She uses the key and gets her cipher. Yes, she sends the cipher to Bob. Bob uses his decryption algorithm, the key he has, and he gets a message. Here, as always, we have attacker that is eavesdropping on the message and wants to get it. Yes, so here is the scheme, and the only obligatory thing is when we are decrypting the cipher, we have to get our message back. Yes. So was offered one-time pad. It's very interesting crypto scheme. It's the only one absolutely secret with perfect secrecy scheme in the world. And how it works? Yes, here we generate the key with generation algorithm, and afterwards encryption is very easy. We just take the key and XOR it with the message. And decryption is the same. We XOR key and the cipher. So here is how encryption, how XOR works. Yes, when we XOR 0 with 1, we get 1, 0, 0, we get 0, 1 and 1, 0. And the only issue is that when we XOR the same values, we get 0, yes? And here we can verify the correctness. To decrypt, we XOR k with a cipher. What is cipher? Cipher is k XOR m. K and k XOR k is 0. And afterwards, we are only with a message, yes? So here is illustrated how it works. Here is n-bit key, n-bit message. It's XORed bit by byte, and afterwards we get the cipher. Its length is also n-bit. Okay, it's the cipher with perfect secrecy. It's so good, it's so nice to implement. Why it is not used today in real life? Yes, because it has two drawbacks. The first one is that the size of the key must be the same as the message size is. Yes, and so usually in the practice we encrypt really big messages, so the key must be also really big. And the second problem is that we need one-time key. What does it mean? So for every message, we need the unique key, yes? So let's talk about the second problem. Let's intuitively understand why it is like this. So here we have C1. So how to get it? We XOR key with the message, with the first message, but key is the same in both cases. C2 is key XOR M2, and afterwards we XOR, yes, these values. And what we get? K XOR M1 XOR K XOR M2, K XOR K is 0, M1 XOR M2 is M1 XOR M2. So when we XOR two ciphers, we get the XOR of messages. So we found some kind of relation between these two messages. Maybe it seems to be nothing, but even for my students, I give this task, and decrypting, and when you have the sufficient amount of messages, of ciphers, it is very easy to decrypt absolutely the whole text. So let's understand what is PRG, pseudo-random number generator, yes. So how it works? It's some kind of function. It gets the seed, the little one, the smaller one, and it gets as the input to generator, and afterwards we get the output. And as it's illustrated, output is much bigger. No, it's bigger than the input. It's the idea. So we said that the key must be of the same size as the message, and it was a problem. So let's integrate our PRG to one-time pad. What we get? We have the little key, that is n bits. We put, and the message is p bits, and p bits is and p is much more than n. So we put our key to generator and get the pseudo key that's only of the size of p. And now we can XOR it with our message normally, and can the ciphertext that its length also will be of size p. Yes, of course, in this case we don't have already perfect secrecy. But in this case, we have computational secrecy, but it works like this, yes? So afterwards was a revolution. We got the public key encryption scheme. How it works? There is a public key. By means of public key, Bob encrypts his message. So to encrypt the message, everybody can. Afterwards, he sends this message to Alice, and Alice must have her secret key to decrypt the message. So only the person who has the secret key, the private key, only he can decrypt the message. So she gets the message and decrypts it with her algorithm. And the most obvious example of public key and crypto system is RSA. That is our problem today, and we will talk about it. It's used almost in all the products. So how it works? Yes, we have, let's say like this, we have three numbers, N, E, and D. The public key is N and D, and our secret key is D, yes? So Alice has public key, she encrypts the message, sends to Bob, and Bob, using his private key, secret key D, decrypts the message, yes? Okay, that's the idea. Okay, when we began to work all of this, when we saw the article that Google and D-Wave signed the contract that they are working together on creating the new quantum processor. D-Wave is an organization that is working very seriously on creating quantum processor. It has already D-Wave 2X. It's very powerful processor. And so they signed the contract that they will work together. As we said, RSA crypto system is used very widely today. It's used in operating systems from Microsoft, Apple, Sun, Novell, in all operating systems. Yes, she is also used for cryptographic primitives in hardware. She is a part of communication protocols like SSL, S1, and so on. Yes, and quantum computers can easily break it. How they break it? They can easily solve the factorization problem. And it's a great problem, yes, today, that it will break RSA, and a lot of products will be really vulnerable. So we can see that RSA Be Safe is used today by 500 million users around the world, yes. And it uses RSA algorithm. So RSA algorithm is the mostly used algorithm today. So as we said, it will cause complete house breaking this RSA, yes. What to do? Okay, we have today RSA alternatives. I will talk today about, I will just describe shortly basic of them, and afterwards we will make the research seriously on two of them. So the first one is hash-based digital signature scheme. I will not talk a lot about it now, because I will talk really a lot about it very soon. So its security depends on the hash functions that it uses, yes? Another one is code-based public key crypto system. The obvious example of it is Merkle's crypto system, yes? So very quickly, how it works. It has the public key, GNU10, and the private key is SGP. Yeah. Okay, so GN is generator matrix that, so generator metric for code C, and this code is capable to fix T errors. Yes, here is our T. S is random non-singular matrix. P is permutation matrix, and to get GNU, we just multiply all these matrices, yes? To get the cipher, we calculate this zip, and sorry. Okay, we calculate this zip, and afterwards we generate the vector v, where it is, here it is error vector v, and we add it to zip and get the cipher. To decrypt, first of all, we calculate zip, afterwards we calculate mu, and afterwards m. I will not talk a lot about it today, because we have to review other systems on which we have the research focus today. Another one is, the third one is Lattice-based crypto system. It's very interesting crypto system. It's very interesting representative because its security is based on the worst case hardness. One of these examples is short vector problem, SVP problem, or finding closest vector problem. I will talk much more about it today. And another one is very interesting but very, very complicated representative multivariate public key crypto system. So it has a set of quadratic polynomials over some finite field, and it's based on NP hardness of solving these nonlinear equations. It lacks a lot of proofs of security. And to prove all this security stuff, we need a specialist expert in geometric algebra all over the world. There are not too many. Because of it, no, it is a problem. And because of it, we don't have any relevant results. When I visited a lot of conferences, there was written new result in multivariate crypto system. I was sitting in the first row, listening, and nothing new. Okay. So we have 4 alternatives. Everything is okay. What to do? No, the problem we do have, because they are successful attacks on these alternatives. They have efficiency problem. For example, I told that one of the examples, the main example of code-based crypto systems is Merkle's, yes, crypto system. So there was published the attack on it. It was performed by Neil Costigan together with Michael Scott. Also, 4 countries were involved in this process, and they needed 8,000 CPU hours for it. So what scientists responded on it, why it was broken? They said that the size of the key was not enough. So they recommended to enhance the size. So it's already the problem, yes, and afterwards also it has another problem. We cannot encrypt the same message twice. And we cannot encrypt 2 messages when there exists the relation between these 2 messages. Also the efficiency, as you will see afterwards in our research, we have the efficiency problem. And today we already have wonderful results in cryptography and rather good results. And inefficient cryptography can be okay for normal user, but for servers that processes million tasks a second, a minute, yes, for it is a great problem. And already today, Google has some problems with modern cryptography. And so we can imagine what will be if cryptography will be much less efficient. And also we must we must take into consideration the side channel attacks. For example, not so far away ago was published the side channel attacks cache timing attack on RSA and IS. After it, Intel integrated IN's instructions to his processors. Also, on code-based encryption, there was performed the attack concretely on Patterson algorithm. The attack could not restore the key, but it could restore the error vector, and by means of it, it was able to restore the whole message. So we need really to do a very big work to get the new crypto system, yes, because when the new crypto system is got and it's received as a standard, afterwards we have to make the software implementation of it. We need obviously to create a concrete hardware for it. So let's talk now deeply about hash-based digital signature schemes, yes, about hash-based cryptography. And so as I said, it uses hash functions, and its security is based on the security of these functions, yes? So first was offered one-time signature schemes, concretely Lemford signature scheme. How it works? It has the signature key. This key consists of two n lines. Each line has the size n, and to get the verification key, we apply one-way function to it. So here you see x are our signature keys, y are our verification keys, and how they are got? We apply f, one-way function. What is f? F is one-way function that maps n bits to n bits, yes? And in Lamport signature scheme, as you see, we need to apply a function to n times. And we will use this result. So how we assign the message? First of all, we hash it. Why we hash it? Because it can be really big and we need some concrete n size. Yes, we hash it using the hash function. Here is our hash function, h, and it receives on the input the input of arbitrary size, yes, and it maps it to concrete size n. How is it performed the signature? Yes, so we have two n strings of keys, each of length n. Yes, we can say that there is a pair n strings. Yes, pair of n strings. So which we look at the message. If the first bit is 0, we take the first signature key from the pair of the keys. So like this, we check every ith bit. So if ith bit is 0, we take the first key from the pair. If it's 1, we take the second bit from the that pair. Yes. So. And what is the size of the signature is n squared. And in this case, we don't use a function at all. How we verify? Yes, first of all, we hash the message. And afterwards, we'll look at the message and check if the hashed value is equal to corresponding y value, if 0 to the first one in the pair, if 1 to the second one. And one-way function here is used f times. Okay, as we say that signature becomes n squared when the key, so n squared when the hash of the message is n, it's really big. In this case, we have Winternitz one-time signature scheme. It reduces the size a little bit. So here we take the key of the length n pin, so there are n, so there are p lines of length n. Let's see what is this pin. So we divide. We have here internet parameter. It must be more than 2. What is it? It shows how many bits we can sign simultaneously. So P1 is n divided by W, and P2 is calculated like this. And P is the sum of this P1 and P2. So how is done the signature? So first of all, how to get the verification key? Verification key is got like this. So we apply to xi a function 2 to w minus 1 times, yes? And the function f here must be used p to w minus 1 times, yes? So quite a lot. So how we generate a signature? We hash the message, prepend the concrete number of zeros to it. Why? Because it must be divisible by w. So afterwards, we calculate the checksum. We prepend zeros to it to be divisible by w. And 1 minute. Okay, P1 we have, and we divide it into W parts, into P2 parts, and get this case, yes? So signature we calculate like this. And in the worst case, we use our one-way function f, p to w minus 1 times. So let's consider the worst case. And the signature size, as we said, is Pn. We made the analysis, it's less, but it depends on something, and of course it loses the efficiency. So for signature verification, we have to, first of all, we calculate ki's, and afterwards we verify the following equation. If it's true, the signature is true. And for signature verification phase, f must be used p to w minus 1 times. Okay, so we talked about one-time signatures. Here we have a lot of verification keys, and as you know, in cryptography, it's very difficult, problematic to send so many keys. So here is Merkle crypto system that uses one public key, that it is the root of the tree. I will show you how it works. Also, you will see the implementation. So it uses the public key, and you will see how. So how it, and of course, it uses one-time signature, or Lamport or Winternitz. So let's discuss how we generate the key. Yes. First of all, we choose the length of the tree, h, and it must be more or less than 2. Yes. And by means of it, we can sign 2 to h signatures, 2 to h messages. So afterwards, we generate signature keys, not to the h, and calculate the verification keys. How we calculate? But our one-way function, yes. So and here, look. So we calculate we generate this xi's. Afterwards, we get y's. Y's are our signature verification keys, and we hash them. And these hash values are already the leaves of our tree. So how we go up and up? Yes, we have to come to this public. Here the size is 3, so we can sign how many messages? 8. Yes, 2 to the 3. So here we have A00 and A01. We concatenate these two nodes, and hash them. And here A0, A10 is concatenation of these two, but hashed. Afterwards, we calculate this one in the same way. This one is the same, it's concatenation of these two, hashed. And like this, we go up, 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 and here is the pub, yes, our public key. And look, if we begin from here, to go up, this is the main node, and this is the flattened node. So his brother. So we got here, this one is the main, this one is the flattened node, and like this, you will see where we need it. So to sign the message, first of all, we hash it to reduce it to the size of n, and afterward we generate one-time signature. As we saw in previous algorithm, afterwards we choose one of the signature keys, any of them, for example, x, let's call it with the index n, yes, here it is. We calculate yn, and what we do, we go up to the upper node, yes, calculate our public key, and record all the brother nodes. They are called AOSes. All the AOSes I write somewhere, yes. And what is my signature? My signature is one-time signature. It also contains all the AOSes. It contains Y verification key from where I began, and the index of this verification key. Here it is. Signature pub, one-time signature, public key, this index, Y, and all the AOSes. How I verify the signature? First of all, I verify one-time signature. It doesn't depend which one we use, Lamport or Witernitz. Yes, we know how to verify both of them. And afterwards, I have the AOSes. Look, guys, I have the AOSes. So I calculate the hash of it. I know it. I know AOS. It's in my public key. I concatenate them, calculate it. This one I know, it's written, and again there, and I calculate my public key, and check if it is the same, if one-time signature is okay, if public key is the same, so the signature is verified. Okay, everything is well. It was some kind of introduction. Now, what we did. This one is also the famous result, because it's a problem to have to store so many private keys. So for this is used pseudo-random number generator that we looked through today. So we store only the seed. Afterwards, we apply pseudo-random number generator to the seed and get the next seed and one random number. So here, how it works, it's applied to our seed, we get the new seed and one random number, and one new random number, yes? So here it is. Here, it's illustrated how it works. I have the seed, I get the new seed, and I calculate all these x, y's. Here is the problem. It's the official result published by Bernstein, but here is the problem that quantum computer can break a lot of pseudo-random number generators that are considered safe today. So here implemented the attack on Bloom-Micali generator. It was considered safe and was used in many products. And this attack used Grover's algorithm, its quantum algorithm, and discrete and quantum discrete logarithm. So, and using this method, we can break a lot of pseudo-random number generators that are considered safe today. So what we offer? It was the first our offer in this presentation. We offer to use true random number generator, not pseudo one. What is pseudo? Pseudo is not random. It looks like random very much. So if we check it according the tests that exist, we cannot distinguish it, yes? But here quantum computer distinguished, yes? So, and we advise, here we offer to create a true random number generator using qubits, because we are making it for quantum computers, yes? So we can use qubits, yes? In it. It's already the part of quantum cryptography. What I was talking about was post-quantum, and this is little part of quantum cryptography. We will use some aspects from here. So, and what is important? So, pseudo-random PRNG, pseudo-random number generator, we need twice. First, in generation stage, yes, to get all these signature keys, XYs, and also in signature stage to apply these XYs to sign the message, yes? So what is a qubit quickly? So the state of the qubit we can write like this, where alpha and beta are complex numbers, and alpha squared plus beta squared is 1. So when we measure this qubit, it is with probability alpha squared in state 0 and with probability beta squared in state 1. It doesn't know where it is, but when you guys measure it, afterwards it goes to that stage and forgets its previous stage. It's the problem. So, and we need a random number twice. So, like this, we can describe the system of two qubits. The same alpha beta are complex numbers, and the sum of alphas must be squared, must be 1. So, very interesting property of qubits is entanglement, so-called Bell state. What is it? We connect two qubits. One we can take to the universe. It's some kind of so-called teleportation. So we can take it to the universe, and when we measure the first one, the second one we measure and get the opposite state of this first one. So we can recover, we can understand what was the first one. So this Bell state is described like this. What does it mean? It means that when we measure the qubit is with the probability 1 to the 2, yes, probability 0.5 in state 0, and with the same probability, of course, in state 1. So it is random number, yes? So what we do? For key generation, we take the tree of height h, and we can sign 2 to the h documents, yes, using our public key. We connect two qubits using Bell state, yes. We take 2h pairs of the set of qubits, qy and by, yes. And we measure these qubits and use them at x. So we get signature keys. Afterwards, we calculate y as usually, our verification keys, and when we need to sign the message, how we get x, we measure the second part of the qubit. It will be the opposite to z, so we restore the information and sign our message, and that's it. About the security, it's of course secure because we don't change the idea of Merkle, but integrate true random number generator to it. Okay, so here we see that in Lampert one-time signature, one-time function we use 2n times. In signature stage it is not used at all, and to generate and verify the signature, we use it n times, yes? And here are the results for winternits. As we said, in Merkle, we use one-time signature, yes? So, or this, or this. So we must use one-time function this number of times. And also, in Merkle, as you saw, we use a lot of times hash function. We use it this number of times, where h is the height of the tree, yes? So, very serious attention. So we must pay very serious attention to this one-way and hash function. And here, in the beginning, I told about one of the alternatives, Lattice-based, which security is based on worst-case hardness, yes? So here we offer to use Lattice-based signature schemes, Lattice-based construction to construct hash and to construct one-to-one functions. So about the hash function, we have SHA-2 and SHA-3, yes. There is no problem. They aren't broken yet by quantum computers, but we have Grover's algorithm. What it does? It speeds up quadratically the search area. So we have some kind of threat, but about one-to-one function, it's always a problem. So using Lattice is a very good approach, according to our thoughts. So here is our Lattice, yes, and Einstein suggested the family of the hash functions. It's based on SVP, it's security based on shortest vector problem, yes. And to construct a family of these hash functions, we need 4 parameters, where n defines the security of our hash function. As the key, we take the matrix M that is chosen uniformly from ZQ, and hash function maps it to ZQN. So the function maps m log d bits to n log q bits. Now m, of course, must be more than division of these two, and this function is very easy to implement because it uses what? Only multiplication and addition modulo q, yes? So concretely, we propose to use this construction in our Merkle. We propose to use as one-way function and the hash function. For the hash function, we take the key from Z to an M, and it transforms m log b to where it is m log b to n log g bits, and afterwards we calculate it like this. This is our key, our matrix, yes, and x is our message, yes. So we multiply. We multiply them, mod A, of course, and in the case of one-way function, we take the key from this space, and it will transform m log b into m log b. So this will be our one-way function, yes? It has very big efficiency problems, you will see. It's only the idea. It's only the initial result, yes? We are working on further solutions. So, according to the text by combinational method, for security of 100 bits, we must use the key of this size. It's big. You will see that the key is really big. So here I have screenshots, but I don't want the screenshots. Let's run. Let's run and see. So let's begin. This is our Merkle, just implemented. So here, for qubit measurements, there is just a simulation using pseudo-random number generator. And so, as you can see, Wow, why doesn't it take 1 minute? It appeared. Oh, here it is somewhere. 1 minute. Can we open it? Thank you, thank you, thank you. No. I need this. This I had. Yes. Here it is. Yes. And can we make it bigger? It will be just difficult for me now to show. I will look here also. 1 minute. Because I don't see it here. So here is the length of signature. As you see, is very big. The message was used 128 bits to sign. But the encryption time is rather good. Signature time, verification time is also good. Here, one-time signature is checked, and the public key is checked. And 1 minute. Now the second one. Here I implemented the hash function using lattices. Rather interesting, by the way. As you can see, okay, let's run it. Here is the key. Rather big matrix. Yes. Oh, I used it using the lists, and the message is the same: 128 bits. And as you see, the key is needed rather big. So, and as you see, it hashed it to 33 bits. Let's now see one-to-way function. What is the difference? The key I took I generated the matrix key of the different size. Yes. And let's run it. So, as you see, it mapped it 128 to 128, as it was supposed to do. And as you see, the key is really big. And the last one is integrated one-to-way function and hash function to our schema. I thought I will not integrate it, but 2 days ago I made it in night. So let's run it also. So the same script that we had in the first one. And here, no, the final length is the same because the script is the same, yes. And of course, our big key, very big matrix for the key. It's its efficiency problem. No, for further, we use ideal matrices, but not for now. So, and we use different keys, as you see, for one-way and for hash. And verification and decryption time is also rather good, because we said that it is rather easy. It uses nothing but multiplication and addition modulo, yes. Okay, where is my presentation? Back, and I finish. Ah, this is good. This shows, well, I don't see it, of course, but okay. You see it. 1 minute, sorry. Okay, nothing is left. And that's it. So it was our latest result, yes. And also we have made the first cybersecurity practical and scientific journal in Georgian. I ask all of you to publish the articles in the journal. It's for free. You are just helping us, guys. We need as more publications. It's better for us. we need good publications for Scopus in the future and also for Georgian community. Here are my contacts. If some of you is interested in post-quantum cryptography, quantum cryptography researches, come to me or today or tomorrow. I will be glad to extend the team. The projects we also always have. We are working, and I will be very glad to discuss the issues, also the development of different penetration tools and so on. I am open for conversation. Thank you very much. Some
we
questions?
have questions here, okay? Yeah.
Besides this algorithm, are there any other post-quantum algorithms that are currently in work for the modern era?
Quantum algorithms that
in
break,
cryptography.
yes?
Yeah.
But there are two main algorithms, Grover and Shor's one. Shor's is problematic because it solves the factorization problem, and Grover algorithm is less problematic, but it only has quadratic speedup. So when you have a quantum computer, when we have this quantum computer, yes, and if you begin to check email or something like this, it will be even much more slow than normal computer. So only in concrete calculations, it is faster.
I see that there are lots of algorithms that will probably be developed, but they will combine the classic cryptography with some quantum parts.
Of course, usually with these two algorithms.
Okay.
Mm-hmm.
Thank you. We have a question there.
Hi, Maxim. Really good presentation, dude. So I have a question, but it takes some time in order to compile for me. So you mentioned the true random number generator that you use. And also you mentioned the D-Wave quantum computer of IBM or Google. And I was wondering how these two connect, because my understanding is that the D-Wave quantum computer uses not the standard quantum physics, but instead of that it uses something like something with matter, like a condensed matter physics or something like that, which is a little bit different with the calculation of waves.
Yes, quantum computer D-Wave uses a little bit different algorithms. For example, the computers that are today in Google, they don't have yet Grover and Shor algorithm. As I know, they didn't have it before. Maybe today they made, but they don't have. And what's about random number generator? Yes, they exist. Quantum random number generators already for sale, the commercial ones. I didn't try them by myself in practice. And by the way, they are not too expensive ones. And they use this. They are not from D-Wave.
Yeah,
they are not from
that
D-Wave.
was my question, because I don't see the connection.
And D-Wave is the global manufacturer of quantum processors. And when we saw this article, we began to work. But random number generator, it's already our after result. Theoretical one, of course, because of it we made the simulation.
Yeah, and D-Wave is mostly used to prove theoretical, with putting these gates here and there.
Yes. For now, yes.
Okay. Yeah, thanks. Your math is awesome, dude.
Thank you. We have a question in the second row.
Have you tried to push these ideas to cryptocurrency community? Because it's the great way to battle test new cryptography. There is then big financial incentive to break it, or if it's not broken, then maybe it's ultimately a good idea.
So when it was the boom of this quantum currency, we offered it to Bitcoin, not to Bitcoin, but to some organization that was interested. It's a global government organization that was interested in Bitcoins, and we offered them the new digital signatures, because Bitcoin uses digital signatures and use concretely RSA for it, and we offered our digital signatures, but didn't get finances because it already was finish of boom. We were a little bit late,
Maybe on the next bubble.
maybe.
And we will take our last question right here. Or maybe, okay. Yeah.
Hello.
Hello.
Interesting presentation. My question for you is, I saw that you developed your own hashing function, which was basically a product, and when on each you applied a modular function. Then you came up with a result that would prove that this is safe. But I'm curious, how did you do that? I mean, isn't since it's using a modular function, isn't it open to collisions?
About the collisions, yes. In HTI construction, there can be found the collision. I will explain you why. I said that we are working on forward optimization of it. It has, as you saw, the efficiency problems, yes, very big key. We said we will use ideal matrices. Afterwards, we will use Swift not to get these collisions. And why the collisions is got, I will explain. It's very easy. So when it's multiplied, yes, you don't get concretely the concrete size because it changes. Yes, because you from binary take it to integer, you multiply and so on. And afterwards you add, you extend it a little bit. And when you extend, if the size is not big enough, you can get the collision.
Also, I saw that basically you're saying that you're using a Bell state in order to have a true random generator. But
Yes.
This has to be generated by a computer, right? By a quantum computer.
Yes,
And
yes.
I guess what I'm trying to say is that the quantum verification problem is that it's solved. So this would be at the core of your algorithm. So you're saying this algorithm is going to be safe if the quantum verification problem is solved. But you do not have any way to prove that number is indeed truly random because you do not have a way to test that on a quantum computer.
I understand, but all this we know theoretically. Also Grover's algorithm, also Shor's algorithm. By now, all these are theoretical results, yes? Because of it, I use the simulation even when the quantum key distribution, yes? They are already the equipment that distribute quantum key. They are got the test. For example, Belarus, our friends in Belarus bought it already in one of the universities, and it is on the very limited distance for now. So there are experiments, and so on.
Thank you for your presentation again.
Thank you.
Thank you. And the last question, if it's still valid.
Please.
Hello. Like in one of the few slides, you discussed the difficulty of the mathematical problem that the multivariate system is based on. So, like, I don't know, can you please go back to that slide?
Of multivariate, yes?
Yes.